Hello, thank you all for joining us today. The theme of this session is Advanced Modeling and Water Quality Monitoring for Optimizing Water Resource Management. My name is Tolessa Deksissa. I'm a moderator of this session. Before we start sharing with you the progress of our research funding, let me give you a brief introduction. As you all know, water is life, and improving river basin management is crucial for sustaining essential service of river for growing population and the warming climate. As you all know, water quantity and water quality requirement changes as the growth of the population, the natural and the man-made disaster, including the pandemic period. Many parts of the world have been affected due to the lack of available safe and clean water. Many life has been affected due to this. So the purpose of this presentation is actually to give you a highlight of progress made in research work at University of District of Columbia and Catholic University of America with regard to the Potomac River Basin management. The issue in the Potomac River Basin water resource management is one, quantity, second is quality. With respect to quantity, during drought period, 3/4 of Washington DC metro area depend on the low flow forecast and the corporate water supply operations. During the very low flow, the water is released from the reservoir to meet the need of the downstream. When it comes to water quality, regardless of concerted effect of the states and the utilities in reducing the nutrient load, the Chesapeake Bay water quality continue deteriorating or not much improvement due to algal bloom and dead zone. To address this issue, the University District of Columbia of the Water Resource Research Institute continue supporting the research projects at the University of the District of Columbia and Catholic University of America and developing the capacity of forecasting and also water quality monitoring at UDC. Our research finding is and effort, we successfully developed an environmental quality testing laboratory that is nationally accredited at the University of the District of Columbia that can actually test water and soil quality. And the second, we developed 3 water quantity and quality models, which includes the project that was implemented and completed by Dr. Arash Masuti on green infrastructure flexible model and analytical probabilistic model developed by Dr. Pradeep Behera at UTC, and the last but not least, machine learning and artificial intelligence application for water resource optimization by Dr. Nian, Ashlee, Zhang. 3 of our researchers or engineers going to share with you today in depth about their research findings and the progress made. I appreciate your participation, and I will look forward for your question and comment at the end of this presentation. Thank you.
Talk about this tool called Green Infrastructure Flexible Model that we've been working on in the past few years. So GIFMOD is a flexible multi-physics tool for modeling the effectiveness of stormwater green infrastructure. I mean, it can be also used for other water systems as well. GIFMod can dynamically model water systems, both in terms of hydraulics as well as water quality. It can be used for a variety of applications, including modeling water quality, hydraulics, biogeochemical cycling in best management practices, green infrastructures, stormwater control measures, low impact development, stream restoration. It can be used for agricultural BMPs as well as urban stormwater control measures. It can be used to model hydraulic and water quality in streams, lakes, wetlands, catchment stream systems. It can also be used to explain the results of both field scale or lab scale experiments. It has been used for water and wastewater treatment processes. GIFMod has a graphical user interface, so users can basically build their models using sort of as a kind of a drag and drop scheme. It's written with C++ programming language. It has a graphical user interface that is written using Qt library. And it also has an API, which means that people can essentially use the computational engine in their programs as a sort of library. So the way GIFMod works is basically users can create their model using a number of blocks. Each block can represent different parts of the media. And then the blocks are connected using something we call connectors that can represent the interfaces between the media parts, or they can represent other features such as pipes, controlled flow, wears, and things of that nature. The media types that can be considered in GIFMod include soil, groundwater, surface water ponds, streams, overland flow, and then aggregate layers, which are basically storage layers used to store water in green infrastructure systems. Other processes can also be considered in addition to flow. They include transport, particle transport or colloid transport, aeration or external flux, evapotranspiration. There are a number of evapotranspiration models implemented and available. Plant uptake, plant growth, and the build up and wash off of pollutants from the surfaces. So now in this presentation, I just want to go through this application of GIFMod that we recently did. We applied the GIFMod to evaluate the effectiveness of green infrastructure implementation in a watershed nearby Washington, D.C. Called Sligo Creek. It's Sligo Creek basically in Maryland, but it's in the vicinity of District of Columbia. So what we did was that we actually discretized the watershed into a number of sub-watersheds, as you can see here. And we basically created a conceptual model representing the stream network of the creek itself, the contributing catchments for each of these subcatchments. Each subcatchment was divided into the pervious and impervious zones. And then we also considered soil layer in order to be able to model infiltration and also groundwater. And this way we can also consider surface water, groundwater interaction. We calibrated the model using the data, hydraulic data or flow data available on Sligo Creek. And then based on the calibrated model, we started implementing a range of scenarios of green infrastructure. So basically we considered 4 different designs. Here I'm showing only 2 of them. The 4 different designs basically represent different types of green infrastructure, including bioretention systems, infiltration-based systems, stormwater ponds, and such. Then we ran the model we actually implemented different levels of these GIs. Of course, we have a pre-development scenario, and then we had 3 other scenarios representing 10% implementation, which means that 10% of runoff is diverted to the GI, or 50% and 90%. And we came up with, we actually evaluated the effectiveness in terms of volume reduction, peak reduction, and groundwater recharge. So as you can see, we can see the volume reduction here as a result of each of the scenarios, each of the designs, and also each of the levels of implementation. Currently, we are working to couple GIFMOD with reinforcement learning to be able to find out whether we can come up with optimal basically operation or smart control of green infrastructure at the watershed scale in an integrated way to basically minimize the cost and maximize the long-term effectiveness of GIs at watershed scale. If you're interested in GIFMOD, please go to www.gifmod.com. There are a lot of resources over there. There are worked examples on a variety of applications. There's also a YouTube channel that you can check, and there are a lot of instructional videos on how to use GIFMOD for a variety of applications. And after this session, of course, if you have any questions about GIFMOD, please feel free to contact me at my email address, and I will appreciate any questions you may have about the program. Thank you very much and have a great day.
Hello, everybody. My name is Pradeep Behera. I'm going to talk about analytical probabilistic models for runoff quantity and quality. The assessment of runoff quantity and quality has been a major challenge for many urbanized and urbanizing watersheds. The estimation of runoff volumes and pollutant loads from non-point sources, specifically from urban watersheds, is very complex due to a number of factors: the random nature of rainfall, the variation of runoff characteristics, pollutant buildup, pollutant wash-off, and overall complexity of urban watersheds. Therefore, it is appropriate to analyze the urban stormwater management specifically from quantity and quality point of view in a probabilistic setting. So the motivation of this probabilistic approach is this: as an alternative to continuous simulations, analytical probabilistic models have been proposed for analyzing urban runoff quality and quantity issues. As we know, the climate change has been impacting not only our urban infrastructure, at the same time, the analysis of runoff quantity and quality for urban watersheds. So, in this research, as an alternative approach to continuous simulations, analytical probabilistic models have been proposed to analyze urban runoff quantity control and runoff quality control. Based on the concepts of statistics and probability theory, specifically derived distribution theory, these models have been derived from the probabilistic characteristics of system input. In this case, system input means its rainfall characteristics, using functional relationship between input and output. The transformation functions, for example, can be used between rainfall and runoff and build-up and wash-up mechanisms, similar to continuous simulation model such as US EPA SWIM models. Okay. Now, these models requires the analysis of input meteorology. So in order to do that, what we need to do, we have to take the long-term rainfall record and define an inter-event time, that is between 2 consecutive events, what should be the time gap that will distinguish 2 consecutive events or 2 separate events. Now, once we define the ITD, then the entire long-term rainfall record can be discretized into time series of rainfall characteristics, such as rainfall volume, rainfall duration, rainfall intensity, and inter-event time. So once you have this time series, you fit a probability density functions. So you develop the probabilistic characteristic of input functions and use the transfer functions between input and output and derive the output functions. In this case, we have developed simplified equations for runoff volume and runoff pollutant loads. And these analytical models are very useful for planning, analysis, and design of urban stormwater management systems. And specifically, the recent emphasis of ecosystem approach, such as low impact development, we need to analyze volumetric hydrology over a long period of time. Thank you.
The title of my talk is Development of a Drought Prediction System based on Long Short-Term Memory Networks, LSTM. As stream flow quantity and drought problem become increasingly severe, it's imperative than ever to seek next-generation machine learning models and learning algorithms which can provide accurate prediction. Reliable prediction of drought variables, such as precipitations, soil moisture, and stream flow has been a significant challenge for water resources, professionals, and water management due to their random and nonlinear nature. This project proposes a long short-term memory network-based deep learning method to predict historical monthly soil moisture time series data. The proposed LSTM model learns to predict the value of the next time step based on both observed values and the predicted values. This is a flowchart of LSTM model. It consists of 4 layers. We customized the dynamic LSTM model to solve the soil moisture prediction problem. The first layer at the very bottom is the input layer. It provides the feature sequences. And the second layer is the LSTM layer. At each time step, we predict the value of the next time step using the observed or predicted value of the predicted time step. The mathematical formulation can be expressed in this formula. The predicted yt equal to the function yt minus 1, yt minus 2 to yt minus d. D is the time delay. And the third layer is the hidden layer. It's fully connected. It used to calculate the predicted value. And the final layer is the output layer. It contains the predicted sequence. We use the MERA dataset, which provides historic soil moisture values from 1980 to 2012 to predict the future soil moisture. From the simulation results, in which the network is updated with previous prediction values, we compare the predicted response with the test data. The error has been expressed in root mean square error, which is as low as 0.019717. In order to compare with the network state, which is updated experiment, which the network is updated with accurate value, which is the observed value. By compare the predicted response with the test data, we find the root mean square error has dropped to 0.0087584. So our conclusion is that we find that the predictions are more accurate when updating the network state with observed values instead of the predicted values. The future study will be to obtain the soil moisture index and use it to predict the drought index. The drought prediction system will have profound impact to the water resources management, agriculture, and urban construction. The acknowledgement, we want to acknowledge the support from USGS grant number 2020 DC 142B. Thank you very much.